let's review a couple of stuff. If I have a set of linear equations in the form of ax equal b and b is non-zero, and I'm looking for x, it's pretty easy to find the x. All I had to do is make this matrix a square, so I have to multiply it by a transpose, so it get n by n, and then I can multiply it by the inverse of this matrix, so I get rid of this term, and then x equal to this term, which is called least square as well. If I have a homogeneous set of equations, that means the other side is zero. Well, if I do this, I will get one obvious answer, which is x equal to 0. So I can imagine here everything gonna be 0. So I cannot do the least square. I have to compute the SVD, and I have to decompose A to 3 elements, use U sigma and V transpose. This is a translation, this is a scaling, and this is the, again, a rotation. And the answer to our system of linear equation is the last column of V. So this is something you should know in advance. Okay, let's get started. So let's first review the intrinsic and extrinsic matrices. Let's see what are they. Imagine this is your camera, and this is the central projection, or the pinhole on your camera where the ray of light goes through your camera. And here is your sensor, or your image plane, which we usually imagine it the other side of the sensor, other side of this center of projection, just because everything gonna be upside down and everything gonna be minus, so we just flip it on the other side, so everything gonna be positive. So you have an object like this, then the ray of light gonna go through the center of projection and gonna hit the sensor plane here, and also one ray which is go directly through the center of projection, gonna continue like this. So you have 2 points, and you will get a shape like this from the 3D object in the world. So if you write the equation here for these two triangles, you can easily see y over the f is equal to y over the z, and this is same for the x. So if I want to write it in the shape of a matrix multiplication, I can see that I can write it in such a form. If I want to write it in a homogeneous form, it means I have to add another dimension here. I have to add the last column here with 0, 0, 0, so I can still get the same result. So the point that I have here, the point is in the coordination of camera. That means x, y, z are the camera coordinate. Okay, now let's say the point is not in the camera coordinate, but it's in some arbitrary coordinate, which we usually call it world coordinate. Sorry, this slide. Okay, so imagine this is your world coordinate. This is a point P, and we know the position of this point in this frame. And we also know we can relate any two frame by a rotation and translation. And this is your camera coordinate. This is the center of projection, or the pinhole in your camera, and the imager is in the other side, but as I said, we flip it on the front side. So if we know the position of the point in this frame, the world coordinate, and we want to find it on the camera coordinate, all we have to do is multiply by a rotation matrix and translate it. And if I want to write it in the form of homogeneous x, y, z ones, I can easily write it down in a 4x4 matrix. This is a matrix that you have seen a lot, 4x4 transformation matrix, which consists of rotation and translation, which give you the position of the point in the camera coordinate. Okay, now I have the position of a point in the camera coordinate. If I multiply it by the matrix that I had in the previous slide, I can get the point in the image plane. So all I had to do is multiply this by this, and then again by this matrix. And you know that we can multiply this by this or this by this. So first I multiply these two matrices. If you multiply these two matrices, which is kind of difficult because this is 3 by 4, this is 4 by 4, but you can see the first row is identity matrix, here 3 by 3 identity matrix. The first row going to be 1 and the other going to be 0, which when you multiply it by R11 give you R11. It's the same for R12, R13, and also for the third row is the same. So if you multiply, you can see you will get 3 by 4 matrices, which is 3 by 3 here is R, and the last column is T. So this is called projection matrix. This is a matrix that relates any point, any arbitrary point in world coordinate to somewhere in the camera frame. Of course, there's another way for writing this, but I will come back in a second. So keep in mind the number 1 here. Okay, now imagine we are looking to the frame that we had here, the sensor, from the side. So the z-axis is perpendicular to this plane, and this is the arrow that we used to see in the previous slide. So here in my sensor consists of a set of pixels or cells. And when you have a set of cells like this, you usually use a matrix coordinate, which 0, 0 is here, and these are the rows and these are the columns, and here you have a Euclidean coordinates. So when the rays hit the image plane here, 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 these pixels gonna turn on, and you have to somehow relate the pose of your object in the Euclidean space to some matrices for. So let's say we have a sensor consists of 640 pixels in the width and 480 in the height, and let's say it's 10 millimeter by 10 millimeter, which is a very poor camera, but it's a very typical configuration, 640 by 480. And V increase in this direction and U in this direction. That means U gives you the row and V gives you the column. Now let's say in our Euclidean space, this point is 2 millimeter by 4 millimeter, 2 millimeter to the forward and 4 millimeter in the Y direction. Now you are interested to know which pixels are turned on. So here's tip number 1. Actually, what you get, as I said, is this arrow upside down because the sensor frame is in the sensor is in the other side of the coordinate system, but we flip it. So we are actually computing the arrow upside down. If you want to get exactly this, you have to put a minus sign. I will tell you here in a second. So as I said, I have 640 pixels here. In the X direction with in 10 millimeter. That means in every millimeter I have 64 pixels. Now I have to go 2 millimeter forward. It means 2 times multiple by 640 over 10. That's how many pixels I have to go forward, plus an offset, because 0, 0 is not here, is here, which is called V0. So the V or the column gonna be this value, and the row very the same. I have 1, 2, 3, 4, 4 millimeter. How many pixels do I have in every millimeter? 48 pixels, and plus an offset because I'm starting from here. And as I said, this is upside down. If I really want to get this, I have to put a minus sign here because I'm gonna subtract it. But as I said, this is give you the flipped object, which camera take care of that. So if you Want to use the OpenCV API, which has something called CV project, which projects something from 3D to 2D, given a camera matrix. This will compute with the plus sign here. The mistake I did was I wanted to get exactly the same image, so I put a minus sign and everything was a little bit different. I will publish my code at the link description at the bottom of the video, and you can see my code, which I did in C++ and eigen and OpenCV. So let's put everything together. I want to get a point from 3D space into some pixels. So I know that if I multiply this by point in the camera frame, X, Y, Z, I have to multiply F multiplied by number of pixels in the height plus V0, and again F multiplied by number of pixels in the width plus U0, which gives me V prime, U prime, and W prime. And if you multiply everything by the third dimension, you will get exactly the same pixel. So this is the intrinsic matrix. When we talk about the OpenCV intrinsic matrix, this is 3x3 matrix, which is for the old camera they put another parameter here, gamma, because the coordinate system might be a little bit tilted and not be exactly parallel to the sensor, which is it's not true for the new cameras, it's only for old cameras. So sometimes here you have some other values. So after calibration, you will get this K. And of course, this value is only for homogeneous coordinates. So if I want to put everything together, I have a matrix which can map something from world coordinate into camera coordinate, and again from camera coordinate to some pixel value. So let's write it in another way. I just show you the equation number 1 in this slide. Here. So let's write it in another form to explicitly express the C, the position of camera. So if I have a point in a world coordinate and I subtract it by the position of the camera and I just rotate it, I will get the point in the camera coordinate. So X in the world coordinate minus position of camera multiplied by relative rotation of the camera relative to the world coordinate, give me the exactly the same point but in the camera coordinate. So if I want to write this in a homogeneous form with X, Y, Z, and W, which is arbitrary, I put 1, I will get such a matrix. R minus R, C, 3 by 3, 3 by 3, 3 by 1 gives me 3 by 1, and this is 4 by 4. So this gives me a point from world coordinate to the camera coordinate. Now let's multiply it by camera matrix that we have earlier to get it in the image plane. So now if I multiply this by this, let's see what will I get. If I multiply this by this, it's again difficult to compute because 3 by 3, 4 by 4, but again if you multiply every row by every column like this, you can almost see you will get R and minus RC again, very similar to what we did earlier. So this gives me R 3 by 3 and minus RC. From 1 we had KRI minus C, And yeah, so that means if I show the equation number 1 here, because these two P are equal, so this T should be equal to R minus C. R minus C, I just factorize the R and put it outside, so KR equal and multiply by this, and I have KRT. So that means that minus RC from this should be equal to T, because both of them P, K, and then this matrix are equal. So minus RC should be T. So this is very important when you decompose in your projection matrix. I did a mistake and I was following, I was decomposing it in this way, and I was getting totally wrong numbers. So if you're calling CV decompose projection matrix, be careful how to use it. I will also put some example in the link in the description. Okay, now we are ready to talk about camera calibration with based on the DLT approach, direct linear transform. So I have a projection matrix. I can map something from war to the image plane. So let's say XYZW is the position of the point. This is 3 by 4, and I get the U prime, V prime, and W prime, which I divided by the third dimension, give me exactly the pixel value that turn on when a ray of light hit the sensor. So U prime is, I can write the P in the form of P1, P2, P3. P1 just the first row, P2 second row, P3 third row, just like that. So just writing, I'm not doing anything special. Okay, U prime is equal to P multiplied by X. You can multiply by the X, this point, this vector. V prime equal to P2 multiplied by this vector, and W prime is equal to this matrix, third row, multiplied by this vector. So just by writing them, multiplying them by this, I can get U multiplied by W prime minus U prime equal to 0, same for the V. So U and V are exactly the pixel value that I turn on. We have them because we can read the data from the sensor. So I just rewrite them like this: U multiplied by W prime, which is P3X, minus by U prime, which is P1X equal to 0, and also for the V. So if I just rearrange all these equations and put P1, P2, P3 in a column vector like this, so this actually should be transposed like this. So if I put everything in a column vector like this, which has 12 rows and 1 column, and I factorize P1 from here and P3, so here I have X multiplied by P1, sorry, minus X multiplied by P1, plus 0 multiplied by P2, plus UX multiplied by P3. And also the same for V, P3, P2, P3, P2, the coefficient is X and V, X. I will get such a matrix. So 12 by 1, and here I have 2 rows. For every point, I will get 2 points. So if I have at least 6 points, which are not in the same plane, because if they are in the same plane, then I will have I will reduce the rank of this matrix and I cannot solve it easily. So if I have 12 points, sorry, 6 points, every point give me 2 linear equation like this. So I can get a 12 by 12 matrices. I have enough equation to solve this with the SVD. So here is just rewriting this matrix. X is actually this X, 4 by 1. So it has minus X minus Y minus Z, zeros, and U multiplied by X, which is give me UX, UY, UZ, and the fourth one is a 1, W. So again, sorry, here should be P transpose. So with 6 points, I will get 12 equation. I decompose it. The last column of the V transpose is the answer to our system. So this is a Python notation. I will get the last columns of this, and then I will get the H. Okay, so decomposing the projection matrix. I have equation of projection matrix K, intrinsic parameters are rotation, I identity 3 by 1 and minus 3, position of the camera is a 3 by 1 equal to H, which is again 3 by 4. I can see it as 2 matrices, one 3 by 3, one 3 by 1, one column. So because these 2 matrices are equal, every element of them should be equal. So this 3 by 3 part should be equal to 3 by 3 part here, and 3 by 1 should be equal to 3 by 1 on the other side. If I just multiply this by this, KR multiplied by identity, which is again KR, will be equal to H1, and KR multiplied by minus C should be equal to H2. So KR equal to H1. That means if I take the inverse from both sides, I will have RK equal to, sorry, R minus K minus equal to H inverse. And I know I can decompose my matrix into Q and R. If you don't know what Q and R, it's R is an upper triangular matrix that has only values on the upper part, and Q is a matrix that every column is normalized and perpendicular. These 2 matrices, they have exactly the properties of the rotation and intrinsic matrix, because you know the rotation matrix, the values are perpendicular and normalized, and Q and R, and the R is the upper triangular matrix, which is the camera calibration matrix, intrinsic part, which we computed here. You can see it's upper triangular, and this could be our R. So R inverse is Q, and K inverse is R. So this R comes from the QR decomposition. Okay, now the second part, minus K R multiplied by minus C is equal to H2. And we know that KR is actually H1. So if I took the H1 inverse from both sides, I will get the C. So C is equal to minus H1 inverse multiplied by H2. So by having 6 points in the vertical coordinate, by knowing the X and Y and Z, we can find the intrinsic parameter K and R, rotation, and the translation for our camera. Okay, in the next video I will compare this approach with Zhang's algorithm. I have developed the code in OpenCV and also with Eigen, with both of them, and I will put the code in the link in the description. Thank you for your attention.